this app back up again. Now we're going to try to figure out what do these numbers actually mean and what is PyTorch doing when it's computing them. So first of all, this idea of slope.grad, bias.grad is about sensitivity. So just to make this really concrete, let me do this just for the last little bit of it here. I'm going to run this whole thing. I'm going to retain all grads, one sec here. And I'll show you that, that we've actually got a .grad on this sum absolute error. So this is going to tell us how much will the mean absolute error change when we change the sum absolute error by, like, let's do one wiggle on sum absolute error. How much is mean absolute error going to change? Well, it's going to change by 1 over n. So n was 100. It's going to change by 1/100th. So what's that mean? So what this is computing here, so let's say we're going over here to the sum absolute error. We're looking at how much does, I'm going to use the mathy derivative notation here. How much does the mean absolute error change when we change the sum absolute error? And we could see that actually you can just look right here, mean absolute error, sum absolute error, we just divided by n. So we just say that whatever the sum absolute error changes, the mean absolute error changes by 1 over n of that, which we could just say, which we get from there. So that's where this comes from. But now what we really wanted to see was how much does the mean absolute error change when we change the slope or the intercept. And we'll figure that out soon, but I just wanted to get an intuition for how it works down here. To get a little bit more practice with this, let's see how it works for this absolute error. So what do we mean by here? So let me just say, like, how much does the mean absolute error change when we change the absolute error by 1 wiggle? Well, but there's a bunch of numbers here, so what we're going to actually have is a vector of all of the elements of absolute error, and for each one of them is going to tell us how much changing that one element is going to change the result. So let's see. Let me just think through this, and then we can see how it would actually work mathematically. So if I change the absolute error by a little bit, so like let's say we have a bunch of data points. Let's just imagine that we made a bunch of predictions. So we made our predictions well, their predictions are going to be in a line. So our predictions are like this, and then our true values were, some of them were above the line, some of them were below the line. So each one of these predicted points has a corresponding error or residual value. Notice that some of them are positive, some of them are negative. Let's just line them up all right here. So I'm going to do a little coordinate axis here, even though they're not necessarily in order anymore. Actually, let me not coordinate axis these. So we just know that they're in order, but they're not sort of assigned to an x anymore. So some of them are positive, some of them are negative, some of them are a little bit, some of them are a lot positive, some of them are a little bit negative, some of them are a lot negative. Some of them might actually be near 0, but either way, these are the errors. So when we take the absolute error, that's just taking all of these and flipping them up. So all these ones that were negative, we're going to flip positive. So here's use a different color here for a moment. So let's do blue. So our absolute errors, here's our absolute errors are going to be all positives some big, some small. Yep. Okay. So 1 second here.